Distillation and Reflux, Scene 1, Take 1, directed by me.
Okay, what we're going to look at here are these two systems here. This one here is called distillation, and we've got a condenser here connected to by a little T-junction to a pear or teardrop shaped flask, which then would be being heated by a Bunsen burner. This one here is called reflux, and reflux doesn't have all that set up. It's got the heat source, Bunsen burner, the flask, and then just a condenser. They're used for different reasons, but the reason that we use these two systems, or these two setups, is because our organic compounds, in this case we're going to pretend we're oxidising ethanol, are volatile, so they can turn into a gas quite easily. We don't want to lose them into the environment. We want to actually keep them in our flask or collect them in a vessel down here, coming out of the bottom of this. So we want to be able to collect our product, not lose it into the environment. And so that's why we have these systems. If we oxidise ethanol, two possibilities can happen. You can turn it into ethanol, which is the first stage of oxidation, which is the aldehyde. And that one's got quite a low boiling point, only 20 degrees Celsius, which is a lot lower than the ethanol. Ethanol is able to make hydrogen bonds due to the OH group, so it's got a higher than expected boiling point. Ethanol, though, is unable to make the hydrogen bonds because the oxygen's gone from in here. Alright, it's become a double bond down to here. The other possibility is if we keep oxidising ethanol, it turns into ethanoic acid. And it's got a very high boiling point for two reasons. One is it makes what we call a dimer, where two of them join together, and also because you've got the potential for hydrogen bonds to happen because of these two groups here, the double bond to O and the OH here. So if we're wanting just the ethanol, we need some way to remove it before it actually goes on to turn into ethanoic acid. So when we heat it up, we don't want to boil off the ethanol because we need it to react, but we want to get it hot enough that we can collect the ethanol. So for this, we would use distillation. So what we're going to do here is we'd have our oxidising agent, such as acidified permanganate in here. You'd have ethanol, and then of course you'd heat it. We'd heat it until the reading on our thermometer was about 70 degrees Celsius. Hot enough to actually react, but not too hot for the vapours to be primarily ethanol. Because if they were, then they would escape. Looking at this here, if you've got vapour, the vapour can only escape this way here. So if the vapour was just ethanol, so the temperature here is hot enough that you can have it reacting, but not so hot that the ethanol is all a vapour, then that vapour would come down into the condenser. What we have is coming in here is going to be cold water. Okay, so it's connected to the cold water tap. Sorry, I got that the wrong one. Coming in here will be the cold water at the bottom. The cold water goes around an outside tube, and in doing so cools down the inner tube, which has got the vapour. And of course if you cool it down, the particles will slow down and recondense, hence this being a condenser, will recondense back into a liquid, and the ethanol will collect out of here. The only issue with collecting ethanol is its boiling point is 20 degrees, so you'd need the room to be colder than that. Otherwise it wouldn't work. Alright? But this system works because as we heat it in here, and we ensure that the temperature stays below the boiling point of ethanol, the vapour of ethanol can come down here, recondense, and be collected in a vessel down here. So that's distillation. We use that when we're trying to collect a product with a lower boiling point than our reagent. But if we look at making ethanoic acid, if we were to do this and just do it in an open vessel, the ethanol would all escape and we wouldn't be able to make much ethanoic acid at all. So what we have to do is a thing called reflux. So again, here we've got our heat source to give us the activation energy and to help speed up our oxidation. We'd have our ethanol and oxidising agent in here. Now though, we're not worried about anything being on the top. You'll notice it's open. Oops, sorry. Notice it's open. But again, you can see we've got a condenser. So it's going to be cooling the solution down. the vapour down. So as we heat this, we are going to have cold water going around the outer tube again, and then coming out at here into the sink. And as any vapour comes up here, it will be cooled down, and it will recondense and fall back into the vessel to continue reacting. This will keep happening until we've got our final product. In this case, it would be ethanoic acid. We may want to put a thermometer in the top here as well to make sure that we aren't going above, basically aren't going above 80 degrees, because we don't want to, at the top, because we don't want to lose all of the things that we're reacting. All right. So if you're wanting a reaction to go to completion, we use reflux. So they both use the idea of a condenser, cold water to cool down the vapour, to turn it back into a liquid. In distillation, it's so that we can collect it in another vessel down here. In reflux, we do it so that it recondenses and falls back into the reaction and continues to react. So they both use the same ideas of distillation, really, so evaporation and condensing, but they use them in different ways. Distillation, when you've got a low boiling point for your desired product. Reflux, which is this one here, when we're after an end product, basically. In this case, it happens to have a very high boiling point.